So hello students, I'm back with another interesting portion, the basic part of digital communication system. The first basic modulation technique which is used in digital communication was PCM, and the full form of the PCM was pulse code modulation. It basically consists of three processes. It undergoes with three processes, that is sampling, quantizing and encoding. What is sampling? Sampling is the process by which few samples are taken from analog message signal, not the full continuous value but just a few samples are taken. Then the part of quantizing. What is quantizing? After sampling, all the sample value are quantized into some quantized level, and then encoding process is that those quantized level values are encoded into digital bits. How it is all these processes are done? So go to the next slide. So there is it is the PCM transmission system block diagram. First of all, source of continuous time message signal. I'm just telling or giving these lectures, or in your telephone system, whatever the speech you give, all these are analog signal, and my voice is the source of continuous time message signal. Now these are passed through the low pass filter, where the cutoff frequency is mentioned here, fc equals to fm. That ensures that the sampling frequency fs should be at least having a value of twice of fm, where fm is the maximum frequency present in the message signal as per the Nyquist criteria. Just it is done just to avoid the aliasing effect. So this kind of low pass filter is also known as anti-aliasing filter or pre-aliasing filter. So after the sampling is done, it is passed to the quantizer to quantize this sample value, and then these are encoded to your digital signal, and the PCM signal is applied to the channel and transmitted. Now sampling, quantizing and encoding, these are the process. The PCM signal is generated by three basic parts or operation, as I have already discussed. The sampling is an operation that generates few sample values of this analog signal, and it is given by flat top PAM signal. How it is done? Just I am doing here. Suppose I have a sine wave of message signal that is continuous in wave, and the sampling signal are the square pulse or rectangular pulse that is consist of value of 101010 and having a very high frequency than the message signal. So how it if I multiply the message signal with your sampling signal, then here it is. This portion is having a value of 1, amplitude 1. If I multiply 1 with some value x, it will give me x. So 1 into x is the value of this message signal at any instant of time, so it will give me x, and here the zeros values are also there. So if I multiply this 0 with any value x, it will give me 0. So this 1 into x is x, so any value here, if I multiply this with 1, so it will give the same value as shown in the sample message signal, as I'm highlighting with these yellow colors. And if I multiply these zeros it is 0, here it is a 0, then another 0. So if I multiply 0 with any message signal, it will be 0. So that's how my sampled signal will look like. So this is basically a pulse amplitude modulation is done. Here it is the types of sampling. First, there are three types: ideal sampling, natural sampling, and flat top sampling. So now go to the ideal sampling. What is done in ideal sampling? These are the circuits, and I just need to multiply this impulse of train of impulse signal with the message signal, and I will get the signal like these pulses, and it will vary. The amplitude of these pulses will vary according to the message signal. And in the natural sampling, as I have already shown this one in the last slide, it will give these values as it is multiplied with the square waves, that is consist of 0 and 1. And now the flat top sampling is almost similar to the natural one, but the top will be flat in that case of each pulses at the output. So here two fates are used, that is sampling switch and discharge switch. It will The capacitor will discharge through this, and the top of the waves will remain flat. So three kinds of sampling are there: ideal sampling, natural sampling, and flat top sampling. Basically flat top sampling is most common. It is done in PCM. Now this is quantizer. Suppose this blue wave is the message signal. I have digitized it. I have sampled it, and these red signals are the samples which I have taken by pulse amplitude modulation. First, at the instant time 0, the sample taken is 5. At the time instant 1, the sample taken is 7, then 6, then 1, then 2, 4, 7, 4, 3, 2, 5. These are the quantization level or voltage level. Now as you can see in the left, the y-axis is valued from 0 to 7, so 8 values are there. So 8 means, what is 8 means 2q. So 2q means the power of 2 is 3. So this is basically the example of a 3-bit PCM. If I increase the number of quantization level, it will become 4 or more further bits. From 0 to 15, it is 4-bit PCM. Beyond 15, it will be 5-bit. Beyond 32, it will be 6-bit, like that. So number of the quantization level increases, the bandwidth also will be increased for PCM. Now this is the process of encoding. The output of the quantizer is one of m possible value signals. So I already discussed m equals to 2 to the power n. So in that case 8 equals to 2 cube, m equals to 2 cube. So 3 the and for encoding if the quantization level is 8 from 0 to 7, so it will be converted into 3-bit PCM like this. For quantization level 7, the coding will be 111. For 6, it is 110. For 5, it is 101. For 4, it is 100. For 3, that is 011. For 2, that is 010. And for 1, it is 001. For 0, it is 000. So in that case, how these binary signals will be transmitted: for 5 it is 101, for 7 it is 111, for 6 it is 110. So this is how your uh, output signal will be generated. Like each and every quantized value will be taken as 3-bit PCM. Each value will be converted into 3-bit digital value. So 11 numbers of samples are transmitted, so 33 bits are used to encode this signal. So this is one of the disadvantage of PCM. The bandwidth requirement is high. To overcome this problem, later delta modulation was built up, but It will be discussed in later videos. So thank you, and hope you would like this very short video. So thank you for listening.